All right, so this is my last talk. This will be the longest talk as well. And for some of you, I think for some of the residents who Dr. Knuckle was here talking to a few weeks ago, some of the slides will actually look a little familiar. At the very beginning, I borrowed a couple slides from him to sort of start us off in this talking about data analysis and interpretation. The basic outline of what I'll be discussing, I'll talk about different types of variables. We'll also talk about different types of statistical tests, kind of the overarching families of tests that there are. We'll talk about some important considerations when thinking about data analysis. We'll get into common tests and some examples of those common tests, and there should be plenty of time for questions as well at the end. So when we think about variables, broadly speaking, they fall into, most of the time, 4 different categories. And it's important when you're thinking about your data to think about which one of these categories your variable might fall into, because that's going to have implications for the test that you choose to analyze your data, but also how you collect the data. And this is certainly relevant to the last lecture on data entry, data management. So variables can, broadly speaking, be continuous, categorical, ordinal, or binary. And we'll go through each one of these 4 and talk about what they mean. So continuous variable exists on a scale that at least theoretically has no bounds. It's called an interval scale, and a variable on an interval scale like this could be 0. It could be really anywhere along here. We could have a decimal value. It doesn't have to be an integer value. So any place on this scale for a continuous variable, right? So we think of age as a continuous variable. You can give your age in months, you can give your age in years, but either way, that would be a continuous variable. Categorical variable would be something like race, favorite color, IOL location. There's a fixed number of categories. An IOL location should be either in the bag, sulcus, ACIOL, scleral fixated, or the patient could be aphakic. We could probably think of some other examples that shouldn't be places where an IOL goes, but these are the primary locations where you might find one, and so this is considered a categorical variable. Categories from which to choose. Favorite color, same kind of thing. An ordinal variable is essentially categorical, but has order to it. So we could talk about an ordinal variable in terms of age ranges like this: less than 5, 5 to 10, greater than 10 years old. An ordinal variable could also be, say we had patient satisfaction scores, and they were from 1 to 4, right? And everybody was supposed to rate how happy they were with their experience getting cataract surgery at Aravind. Well, it's not continuous 1 to 4 because it ends right there at 4. It's not categorical because there's ordering. 3 is more than 2. It denotes better satisfaction. So that would be an ordinal variable as well. And so with an ordinal variable, if you're 4.15 years old, you fall into the first category here. We can see how that works across the spectrum. When it comes to a binary variable, though, by definition, we can call this binary or dichotomous. Really means the same thing. By definition, there's 2 categories. Less than 7 years old, greater than or equal to 7 years old. Male, female. Right, 2 categories. You could say blind, not blind, right? And this becomes important again when we talk about statistical tests, where we might be thinking about our outcome being binary, say, versus continuous, different tests for different types of variables. So now that we have any questions about variable types or what a certain type of data might fall into in terms of categories? So when we think about different types of statistics, there are a few sort of broad families of statistics, and I think some of these terms have been kind of thrown around throughout the day today, and I just want to take a moment to define them. When we talk about descriptive stats, we're really summarizing the sample. So we might say the average age of participants in our sample was 37. That's a descriptive statistic. It's a summary. Inferential statistics estimate how well the conclusions we're making based on our data apply to the world. So this would be like going back to some of our examples from earlier, where we do a Ttest and we say that men and women on average have different heights, right? The population mean is different for height between men and women. It's an inferential type of statistic that got us there. It's not descriptive any longer. We could talk about the mean height in women, the mean height in men, that's descriptive, but it's inferential once we go ahead and start making conclusions about what those data mean for the population. There are analytic statistics. The example here would be, say, regression, which we'll talk about. And this is describing the influence of multiple variables, how they come together. There's agreement statistics. We might have two graders of, say, corneal ulcer depth, and we want to see how well the two graders agree with one another. So there are statistics to look at that, agreement statistics. And there's validity statistics, and this is important if, say, we're developing a new measure. It could be a new measure of IOP, it could be a new quality of life measure, and we want to know how well that measurement tool is measuring whatever it is we're trying to get at, whatever it is we're trying to measure, the underlying construct. So those are validity statistics. I'm going to focus most of what I talk about. I'll talk a little bit about descriptive. Mostly we're going to focus on inferential and analytic statistics, because that's what you'll encounter most in articles you read and also in studies that you're doing. So when it comes to descriptive statistics, we're all probably familiar with how to describe a continuous variable. There are several measures of central tendency, mean, median, and mode. I think most people probably know what those are. But we also tend to describe not just that measure of central tendency, but also how much variation there is in the data. And remember, this is very relevant for a number of reasons, but it's relevant for our hypothesis testing, but also for figuring out a sample size if we go back to the prior lecture. This is analogous to sort of how messy that drawer is when you're trying to find something, right? And the ways we might describe the variation in our data is simply looking at the range. The range of ages in our sample was from 18 to 60, say. The standard deviation, on average, how much a value deviated from the mean. The interquartile range. This is relevant when we're looking at the median especially. It tells us the 25th percentile value to the 75th percentile value. So it gives us a sense of the spread of our data around a median. And then other types of data, categorical, ordinal, binary, are typically described by the number that fall into a particular group and the percentage that they comprise of the total sample. So there's lots of ways to describe data. How do you decide what the best way to describe data is, or should you do it every way that I just named? And there are reasons to choose one or the other. If we look at this data set, sort of an imaginary data set of IOP values arranged in increasing order, we can see that we can easily identify the middle value or the median. We can look at the range and the upper value, the mode, the most commonly reported value. And we can also calculate an interquartile range, so 75%. So for the 25th to 75th percentile is going to be from 16 to 30. Interestingly, we see the mean is greater than the median. And this is something we often see where the mean and the median don't match. And there's a reason for that. So when our data are not perfectly normally distributed, they don't follow that perfect bell curve, we'll see a mismatch between the mean and the median. So in this case, we see a long tail out here to the right. We say that this data is right skewed because of this long tail. And these values out here are very big, right, relative to any other values in our data set. And what they do, because the mean is an unweighted average of all of the values contributing to our data set, they're going to pull our mean towards the tail, right? These big values are going to have a big impact on the mean, and they're going to pull the mean. The median, though, is insensitive to outliers, to extreme values, because it's just the middle value. So it doesn't care if the value above it is 20 or 60, right? If the median is 19, 60 has the same effect on 19 that 20 has on 19, right? We're just looking at what the middle value is when it comes to median. So it can't be pulled by these extreme values like the mean can. So if you see a mean greater than a median, you know that it's going to have a tail out to the right. And the opposite's true if the mean is less than the median. So oftentimes the mean is a good measure of central tendency in big data sets, but with small data sets where you're going to have perhaps more outliers because the data set is small, so even one outlier might be a big deal. And small data sets will oftentimes report the median and the interquartile range because it can be a better measure of central tendency with small data sets especially. So then if you have some of those outliers, what should you do with them? Should you just ignore them in your analysis? Should you throw them out? There's no clear answer here, and there are different ways that one can deal with it. Certainly if you get rid of outliers, you're going to decrease the variability in your estimates, and if you decrease variability, that means good things for your sample size. It means good things for some of your hypothesis testing. However, you're eliminating real data. There are people out there in the world, in our population, and therefore in our sample, that are outliers. And should we really be getting rid of those outliers, or are they important? Sometimes they're the most interesting, and sometimes we need them in our data set. Also, if we're just throwing away values in a very non-systematic way because they seem too big or too small, that's data manipulation, and it raises sort of red flags that, perhaps what you're reporting has been a little manipulated or massaged to fit what you're trying to get at. So in general, we keep outliers in data sets, but there may be some reasons to get rid of outliers in certain situations. The best course of action is outlier prevention and protection. So if we standardize data collection in some of the ways that were discussed in the prior lecture, and if we have an adequate sample size, we're respectively working to prevent outliers that might not be real. Sometimes we get outliers because of sloppy data entry. And with an adequate sample size, the outlier is not going to mean as much. Because remember, even when our data are skewed, most of our data are under this part of the curve, right? So if our sample's big enough, those outliers aren't going to have as profound an effect on our data set. So we can just see here what happens when we exclude values. If we take out this value of 60, it has a small effect on our median, but actually a pretty big effect on our mean. Our mean dropped by 3 by excluding 60. So that just illustrates what might happen if you exclude that value. And certainly if you think it's a data entry error, you should get rid of it. But there are people, as we all know, with pressures of 60. And so getting rid of it might not be appropriate. So another issue that comes up frequently, most people have 2 eyes, right? So what do we do with the fact that we have 2-eye data on most of our patients, many of our patients, depending on the study? The 2 eyes, they sit in the same head, in the same person, and so they're usually strongly correlated. Certainly if you have glaucoma in one eye, you're more likely to have glaucoma in the other eye. If you have diabetic retinopathy in one eye, you're more likely to have it in the other eye. Most of our statistical tests are predicated on the assumption that all of our observations are independent of one another. But certainly, if you look at 2 eyes in one person, those are not independent observations. I don't think anybody could argue otherwise. So can we use our standard statistical tests, or should we do something different? So there are a few options. You can just use one eye as an option. It's not always the most appealing option because you've taken data on both eyes for all of the participants in your study and you have the data, and you likely want to use it. You're going to drop your power if you didn't account for that from the get-go. You might be cutting it in half if you're eliminating one eye from every participant. Another option, depending on what you're doing, is a paired study design. So you could have perhaps an intervention on one eye and not the other eye. Then you have this internal control, and you're able to use potentially both eyes because you're actually comparing them in separate groups rather than tossing them into the same group. 2 data sets, essentially. Or you can adjust for the correlation that's inherent between the 2 eyes belonging to a same person. And there are different ways, we don't have to get too into it, but there are different ways that certainly the biostatisticians can discuss with you of adjusting for that correlation. And essentially what you do is you say that there are multiple levels of our analysis. Yeah, we're interested in the association between intraocular pressure and glaucoma, but we also have this other level to our data set, which is the person level. And so we have to adjust for the fact that there are multiple eyes nested within an individual person. And there are ways of doing that with things called generalized estimating equations and multi-level models. So we all know there are lots of statistical tests out there, and that's why there's lots of fancy software to analyze data. So what tests do you use? And although you have biostatisticians to help you along the way, and they're very, very skilled and knowledgeable, it's good to understand not only for the planning phases, but for the interpretation phase. Because let's not forget, it's your study that you've designed, and you want to be able to interpret the data in the context of your hypothesis and understand the statistical results so that you're able to best determine not only statistical significance, but also clinical significance. So you have to know, first off, very simply, the test that you're running, what's it comparing? Are you going to compare means? Are you going to compare percentages, counts? There are all sorts of things we might choose to compare depending on the data that we have. What are my data like? Are they continuous? If they're continuous, do they follow a normal distribution, that is that bell curve, or a non-normal distribution? And parametric refers to normal and non-parametric to non-normal. Are the data categorical? If so, how many categories, and are they ordered categories? Is it ordinal? Or do they have no order to them, like the lens position, sulcus, posterior chamber, anterior chamber? Are the data longitudinal? That is, do you have repeated measures over time on the same individual? And if so, is your follow-up equal or unequal among participants? Because that's also going to impact the type of statistical test that you choose to use. So, going back to something we talked about earlier, and I think I said earlier that I was going to mention it a few times because I think it's so important. Does anybody remember kind of the precise definition of what a p-value is? Close. I'm sorry? Yeah, so right, so Dr. Swati said how many false positives are we ready to accept? We might get 5 false positives per 100 if our p-value is 0.05 or 5%. And that's that's certainly true, and that's how we think about it in terms of sample size. And then we do the hypothesis test, and what we're really thinking of is the probability of getting an effect as extreme as the one that you found, assuming that our null hypothesis is true. It's a little confusing, but if we assume that the data are normally distributed, there's nothing interesting happening here, right? Nothing interesting. But then you do a study and you find that let me go back to one of these curves here. You find that your data are actually out here in the tail, right? So your data are pretty extreme. They're not following a fairly normal distribution. We can call this fairly normal, not perfectly normal, but they're not following this distribution. You really don't have data out here. Your data are clustered over here. Your mean is right there with a pretty tight standard deviation. That's pretty extreme data, right? And so if this is a picture roughly of your null hypothesis, but your data aren't fitting your null hypothesis, in fact your data are all the way out here, then you might reject this null hypothesis and say, no, my data are extreme. There's something interesting happening here. Right? And that's what the p-value is getting at. It's the probability that if the null were true, if that distribution is what existed, what's the probability that you would actually find the data clustered out there? It's pretty low. It's pretty low, and that's what the p-value is getting at. So then what's a 95% confidence interval? We see that all the time also. Anybody want to try that one? So it means that there's a 95% chance that that interval includes the true population value, right? So we do a study and we say men are on average 1.5 meters tall with a 95% confidence interval from 140 to 160 centimeters. There's a 95% chance that the true answer, of course we don't know the true answer, that's why we did the study, falls between that 140 and 160 centimeters. So this is just another, probably a better illustration than the one I just used a moment ago, that shows us in the null distribution here, right, the normal distribution, this is the most likely observation, right? We can think of this as area under the curve, right? And this is clearly the highest point in our curve. Most likely data point we're gonna see is this. These observations are very, very unlikely if this curve describes our data. But if we reject the null hypothesis, that is, our study pans out to be, let's say, true, right? There's an effect in our study. We reject the null hypothesis. These very unlikely observations are what we're getting. That's what we're finding in our study. Our observed data is out here, and that's our threshold significance, so we reject the null hypothesis in favor of the alternative hypothesis. That is, there is an effect. And then here's the illustration of the 95% confidence interval. If our data is normally distributed with a mean of 4.27, there's a 95% chance that our population mean falls between 2.92 and 5.62. 95% confidence interval. So we have all of these ways of summarizing data, but what do you report when you're writing a paper? Certainly you don't report them all. Rarely do we see the mode reported in a paper, for example. So it's important to report an effect size. So an effect size could be 10% versus 15%, right? 10% of people followed up versus 15% after our intervention. There was the odds ratio was 2.4. We'll talk about odds ratios in a few minutes. There was a difference in the mean IOP of 3.6 millimeters of mercury, right? These are all effect sizes. We should usually report the 95% confidence interval. That gives us a sense of how sure we are about that value, right? We have an odds ratio of 2.4, but is the 95% confidence interval from 0.27 up to 35.6? Or is it from 2.2 to 2.6? We're much more confident if it's a tight confidence interval, right? We're pretty sure of the space that the actual population mean occupies. And then similarly, the difference of the means, we can report what the 95% confidence interval is around that difference. And we should report some sort of result of our significance test. In some cases, the 95% confidence interval will infer the result, the p-value, but oftentimes we'll report a p-value. Questions there? So this is what I was alluding to earlier. So this was a paper published in 2017 and yes, Swati. Yeah. 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 So if we think of the study that you're designing, you want to look at the difference in intraocular pressure outcomes between suture GAT and trabeculectomy. If your hypothesis was, this may not be the best example since you're hypothesizing non-inferiority, which is a little more complex, but let's say our hypothesis was that GAT is even better than trabeculectomy, right? And so you're interested in testing whether or not that's the case. You do your study and you find that your patients that received GAT had a intraocular pressure that was 2 millimeters of mercury lower on average than in trabeculectomy. Your effect size is 2 millimeters of mercury, right? Similarly, if we were to look at if for some reason we hypothesized that, we can use another one of the studies that we've been talking about. How about the screening family members for glaucoma study? Let's say we do this study and we find that among family members, let's say we also screen a bunch of non-family members in the midst of the study, and we find that among family members, the odds of detecting glaucoma is 3 times greater than in non-family members. That's an effect size, an odds ratio. You could also do a longitudinal study where you detect the relative risk of developing keratoconus in individuals with vernal keratoconjunctivitis versus those without vernal keratoconjunctivitis, right? And then you might have a relative risk, another measure of effect size. Correct. That's correct. Perfect. Yes, it gets more complicated, but still, yeah. You can still make one-to-one comparisons. Say you have a 3-arm trial, right? Yeah, I mean, if you have a 3-arm trial where one is getting medication, one is getting GAT, and one is getting trabeculectomy, you may say trabeculectomy is the gold standard. What's my effect size comparing GAT to trabeculectomy? What's my effect size comparing meds? Yeah. Any other questions? So I alluded to this slide earlier, but it'll be even more poignant maybe if I actually read the slide. So this is a recently published article in Ophthalmology, considered by many to be the top journal in our field. Compared with Surgeon 2, Surgeon 1 had a higher proportion of laser suture lysis, 51.8 versus 34.7, p equals 0.02, and higher mean preoperative IOP, 19 plus or minus 8 versus 18 plus or minus 6, p equals 0.24, and had a higher mean preoperative IOP, right? It wasn't significantly higher. Maybe they're taking it to be clinically significant, I'm not sure. But, you know, we had certainly that number and that number are different, but we have a pretty wide range, right, or a lot of variability in our measurements. And so the hypothesis test, the significance test, gave us a p-value of 0.24, yet they're still reporting significance. So it's, you know, we have to be careful with the way we report these things. And even in our top journals, things aren't always reported cleanly. We just have to, as reviewers, as readers, kind of watch out for some of this stuff. So why is it that p is greater than 0.05? You did your study, you put a lot of effort into it, you get the results back from the statistician, and it's a big letdown. P is greater than 0.05. What happened? This is true. This is true. I mean, different tests have different assumptions, and they might be testing something different, right? Some tests are tests of means, some of medians. Yeah. But in general, you know, you did your test, you didn't get a significant result. What might have happened? So it could be that the null hypothesis is true, right? Maybe there is no effect. That's why you didn't find one. Entirely possible. It could be that you have too little power, right? Maybe you weren't powered to detect the size effect that there was. You were powered to detect a giant effect, and there's an effect, but it's smaller. You just didn't have the power to detect that effect. Maybe your study was poorly designed. You know, maybe with a better designed study, you would have found an effect. So I want to point out again that statistical significance does not equate to clinical significance, nor does statistical insignificance. If you find this negative effect, or this p greater than 0.05, doesn't always mean clinical insignificance. If you have a good theoretical basis to keep going with an idea, you shouldn't always be deterred. You know, some of the greatest innovations and greatest findings that we can point to didn't necessarily come easy. It wasn't, I did the study, p was less than 0.05, problem solved. So if you think there's clinical significance, you might want to keep going depending on the question. So theory can really help us to make sense of results. And I'm a big believer that as we design studies, we shouldn't just write the aims page and kind of put things in very textual kind of language. I have 2 whiteboards in my office, and I frequently use these boards to draw relationships between variables as I'm thinking through a study, or as I'm discussing with a resident or with a student what we might want to do. Drawing relationships between variables, it's typically referred to as a DAG, or a directed acyclic graph. And what these lines all show is what we think is happening with our data. And if we draw these graphs out ahead of time, it allows us not only to plan a sophisticated analysis to test what we think is going on with the variables, but it also just allows us to get a better sense of what hypotheses we might make. Maybe there are various hypotheses we want to consider. It also gives us a chance to think about more complex phenomena like mediation, that is, how certain variables are related, not just that they are related. What pathways are they related through? And it also lets us better think about confounding. Confounding is when there's a variable that's related with both your exposure and your outcome. And so confounding may make it look like there's a relationship between an exposure and an outcome when there isn't, or may hide a relationship that really does exist. And so when we draw these kinds of, and there's very sophisticated ways for denoting confounders, moderators, mediators, and we could go into what all these things mean. I talked a bit about that in November when I was here, but I'd be happy to review some of that. But they allow us to kind of depict these relationships, better formulate hypotheses, and then design more sophisticated statistical tests to test our exact, very specific hypothesis. So I encourage you to just, you know, sit there with paper and kind of draw relationships between variables even before you start writing. I find it to be a useful exercise. So, questions about that? Or about confounders, mediators, moderators? Any of that stuff? No? Well, first I feel bummed, right? And then, no, it's, you go back to the data and you see, is there a problem in the data? Sometimes things are coded wrong, right? It happens. So it could be something really simple, where something was coded incorrectly, or interpreted incorrectly during the analysis. And so you just want to correct that mistake. Sometimes there's just no effect. That doesn't mean that we can't report it, though. And in fact, reporting negative effects, although it's more difficult to get them published, is important, right? It keeps other people from spending resources trying to find that same effect that you already showed isn't there. And if it's a really well-designed study with an adequate sample size, and you showed that there's no effect in South India, why is somebody else, say in Chennai, going to repeat the same study? Maybe they're going to repeat it in Beijing because they have a different population, but they might not want to repeat it down the road in Chennai. And so it's important to get that out there. It can be challenging, though, to publish those negative results. That's just sort of a...
Why that is seen like that? Like, when that is a possibility, while we go for publication, why these negative results are not accepted by journalists?
I think they're less exciting, right? No, I mean, seriously, I think they're just less, there's a bias against them. I mean, it's not necessarily... I mean, you could argue about what's more important, right? A positive or a negative result, but they're not viewed as favorably or as worthwhile as positive results. But there is some value to it. There certainly is some value, especially when it comes to resource allocation for future studies. So if you have a study that you think is important to report that negative result on, I would encourage you to try to do so. So we'll get into some specifics of what different tests are. One of the most basic tests that you'll encounter, and many of you are probably familiar with this test, is the Ttest. There are a few different types of Ttests. I'll mention a couple of them. But in essence, what you need to know is that a Ttest is comparing two means, right? So again, I'll go back to the kind of silly example of comparing the mean height of men and the mean height of women. A Ttest would be that would be a perfect test to use for your two samples, so a two-sample Ttest, right? You have a sample of men, a sample of women. Perhaps, though, perhaps you're hypothesizing that the mean height in men is 150 centimeters. You don't care about comparing it to women. That's a one-sample T-test, and you're comparing it against some value that you think might be the hypothesized mean, right? There's also paired T-tests. So let's say we have a whole bunch of people at baseline that come in with a certain mean intraocular pressure. We start them on timolol. We have them come back 30 days later, and we check their intraocular pressure, hopefully just on one eye per person. That would be a paired T-test, right? It's the same people over again. So paired T-test in that case. So all of these three different types of T-tests have a similar set of assumptions. So they all assume continuous data. You can't really take a mean unless your data is continuous anyway. They assume that your data come from a random sample. That is, that you don't have a biased sample. That's not always an assumption that we meet. Even if we take data just from the clinic here, it's not always going to be a simple random sample. It may be the people who were able to wait around longer to be enrolled in our study, for example. That might not be random. There might be some sort of inherent bias to who those people are. All observations should be independent. That means that there shouldn't be two eyes from one individual, for example. The data should, or more specifically the residual, for a T-test, forget that. The data should follow a normal distribution. So the data should be essentially following that bell-shaped curve, right, where the median's in the center and we have two tails without skewed data. There should also be approximately equal variance across samples. So we have a two-sample T-test. The variance shouldn't be very different between the two. That is, the standard deviation shouldn't be grossly different. The T-test in general requires these assumptions, but they can, and you can discuss with the statistician as you're planning your study and as you get your data, some of these can be relaxed a little bit, especially as our sample gets bigger. So this just graphically displays the normal distribution. And when data are normally distributed, 68% will fall within one standard deviation, 95% within two standard deviations, 99.7 within 3 standard deviations. And this is essentially the definition of the normal distribution. As we get to big sample sizes, some people tell you over 30, some people tell you over 50, this becomes a little less relevant. But certainly with a small sample size, we want to check for normality, and there are different statistical tests that we can use to check for normality. So an example might be, and this is an example from a study we published, 65 children with low vision in Coimbatore received telescopes for their low vision. We want to know, did their measured distance acuity improve? I wrote magnifiers here, but I meant telescopes, with the use of telescopes. So this requires a paired t-test, right? It's the same kids. Same kids at baseline, then they get their telescopes, and then vision is rechecked on those exact same children, so it's paired. So in this case, their vision was measured in logmar, and it was 1 at baseline, 1.0, 0.37 with the telescopes. This was an improvement. This is our effect size of 0.63 logmar. That's our effect size. Our 95% confidence interval, we're 95% sure that children in Coimbatore who receive telescopes are going to have a visual improvement of 0.3 to 1 around this mean improvement. And that was statistically significant with a very small p-value. So we concluded that, that with these telescopes, we see visual improvement in these children. Questions about that? So another test that you frequently encounter, probably the other most commonly encountered test, is the chi-squared test. So the chi-squared test tells us if there's a difference between expected and observed frequencies. So for example, we want to know if there's a difference in eye examination rates between diabetics and non-diabetics. So the classic way to set up your data for analysis in a chi-squared test is with what we call a 2x2 table, right? 2 by 2. In the 2x2 table, we're going to enter counts. So we have A number of diabetics who got an eye exam. We have B number who didn't, and the same is true for non-diabetics, C and D. Now, if everything's equal, given however many people are in our sample, 100 people, let's say, if everything's equal, then we would have a certain expected counts with everything being equal in these cells, right? We can guess what we would expect the counts to be. We might expect, say, 25 in each cell if everything's equal. Or if we know there's an 80% rate of eye exams among individuals as a whole, and we want to know if that's split evenly between diabetics and non-diabetics, then our numbers would vary a little bit from that 25, 25, 25, 25. Does that all make sense? So there's expected counts, and then there's counts that you actually measure. Yeah. So the expected counts assume that there's no difference between your categories. The measured counts are what you actually find in your data, right? And you're comparing what you find in your data to the assumption that there's no difference, or to the null hypothesis that there's no difference. So fewer assumptions here, but we know that we need ordinal or categorical or binary data to be able to enter counts into a table. Again, observation should be independent. And for the chi-squared test, our expected cell counts should always be greater than 5. Our expected cell counts. Does that make sense? If it's not greater than 5, there's an alternative test we can use called the Fisher exact test. But you'll see that a little less frequently because usually we're dealing with sample sizes that are large enough that our expected cell counts are going to be greater than 5. But those are the assumptions. So an example would be, and this is a study that we recently published, there were 2007 older adults in the US and they were surveyed on the use of eye care. And we asked if there was, one of the things we asked was if there was a difference between men and women in receipt of eye care. And we defined eye care as getting an eye exam in the past 2 years. So what we found were these numbers. It's pretty tough to glance at these numbers and say if there's a real statistical difference, right? There was a different number of men and women. So we wouldn't necessarily expect these numbers to be the same, even if there's a similar likelihood that men and women get eye exams. It's tough to eyeball it and know what's going on. But what happened was that the observed distribution was that males, 78% had an eye exam in the past 2 years, 87% of women, and that was different than what we would have expected if the two variables, that is gender and receipt of eye care, were independent of each other. There's a dependency between gender and receipt of eye care in our data. Does that make sense? Questions? Swati? Well, we're not expecting 50-50 because more than 50% of people get eye exams, right? So if we go back to the table here, we might know that on average, 75% of people get eye exams, let's say, okay? So we would expect 75-75, 75-75, 25-25, right? Perhaps. But what we find is that so our null distribution, like our null distribution for the t-test was that normal curve, right? Our null distribution hypothesizes that there's no relationship between gender and receipt of eye care. And then we test whether or not that's in fact the case. But our data were more extreme than that. Our data were more extreme than that no association hypothesis. And so we rejected that no association hypothesis. Does that make sense to everybody? So it's going to get a little more complicated. Yeah, please. Yeah, so if we look at this distribution of data, this is what we actually found in our study. Okay, if there's no relationship between eye care and gender, we can calculate what we would expect to find in this cell, this cell, this cell, and this cell, given our sample size. Okay? This number would probably be a little bit higher. This number would probably be a little bit lower, right? Because we would be expecting no difference, and so they would be closer to equivalent. You can imagine a smaller data set in which, when you get towards that, what am I expecting if there's no difference, that a very small number at that point, your expected count could drop below 5, right? Maybe you have a sample size of 20 and you're hypothesizing no difference, right? You could have an expected cell count less than 5 in that case, in which case the chi-square doesn't really hold up. Does that make sense? Or is it still a little unclear? Yeah. Correct. Correct. And the value is a count, right? It's the number of individuals that meet those two criteria, male and got eye care, female and did not get eye care, right? And so the count is that number. Does that make sense now? Or, yeah. Correct, correct. That's right. That's right. The number 5. Exactly, exactly. Oh, wait a minute. Not sure if that's somebody asking a question. Oh, Ashok. He's making a grand entrance. All right. I think we're good. All right. So we'll move on to a couple more complicated tests, but I'm going to try to keep it a little bit higher level when it comes to these tests, but the assumptions get kind of interesting with these. So we'll talk about some of the assumptions and some of the things to look out for, because a lot of people report the results of regression, but it's not always the case that they've checked that all of their assumptions are met and that it's necessarily been interpreted appropriately. So we'll talk about some of that. So when it comes to linear regression, what we're doing is testing the association between a predictor. The predictor could be continuous, binary, ordinal, between a predictor and a continuous outcome. So for example, let's say we want to know for every additional year of age, what is the change in macular thickness. Okay? So we have then a continuous predictor and a continuous outcome. So we could use linear regression to tell us what's going to happen with macular thickness measured on OCT with each change, with each 1 year change in age. All right? So it assumes, again, that we have independent observations. We have one eye from each individual, right? It assumes that our residuals are normally distributed. We'll talk about what a residual is in just a minute. It assumes there's little multicollinearity. So we can have not just one predictor in this model, right? Not just age, but maybe we want to throw male-female in there, and maybe we want to throw in diabetes status, yes or no, and maybe we want to throw in urban or rural residents. Maybe we have a good reason to do that as well. So there's a lot of variables in here, but if those variables are very strongly correlated with one another, that would violate this assumption of little multicollinearity. And the reason that's important is because when there's a lot of multicollinearity, a small change in one of our variables can actually induce, in one of our observations, can induce a really big change in our effect size. So it can unjustifiably impact our model results when there's a lot of multicollinearity. And then there's this thing called homoscedasticity. I won't ask everybody to say that one. And we'll talk about what that is in just a minute also. And we generally, as a rule of thumb, ask that there be about 20 observations per independent variable. When you have fewer observations than that, you get into some hairy situations with your standard errors being a little too big, and therefore your confidence intervals being very wide. So there's a mathematical equation for the linear regression model. It's not necessarily important that you know the equation, but to understand it a little bit is probably worthwhile. This is our dependent variable denoted by y. So in the case of the example I just gave, that would be macular thickness, right? This is, if you imagine us drawing a line with an x-axis and a y-axis, this right here just defines where that line intercepts the y-axis. We'll look at a picture in just a minute. This beta 1 is the slope of our line. And then x is the value of our independent variable. So if we go back again to that macular thickness example, let's just say we have one predictor, age. X would be age. So your equation would be derived from your model. This would be the intercept of your line, the slope of your line, and you would plug in here the person you're interested, that the individual is 45 years old, and you would get a predicted value for what their macular thickness would be from your regression line. So if we look at a regression line, we have a bunch of data points, right, arranged on an x and a y axis. Let's call this macular thickness on the y, age on the x, right? So we measure age for each person and their macular thickness, and we regress one on the other. So we derive a regression line that fits our data. This is our y-intercept, right there, denoted b0. And we have some slope to this line, denoted b1. And for any individual data point, if we plug it in here with x, we get our predicted macular thickness. Does that make sense? Questions about that? Anybody? No. So the equation gets more complicated as we add variables, right? If we want to not just have age as a predictor, but also have gender as a predictor, or have educational attainment as a predictor, or intraocular pressure, it gets more complicated, but the concept is the same. I don't think it's worth going into the math of the more complicated equation, but suffice it to say that it's the same principle. So what then is a residual? I said the residuals should take on that normal bell-shaped distribution. A residual is how far your actually observed data points are from your regression line. So these are the points that actually happened in your data set, right? You actually had someone who was, I don't know, I guess we'll say 3 years old with a macular thickness of 26. Doesn't make a lot of sense, but in that example. But in any case, if you had somebody who fit, you know, they had 3 of something and 26 of the outcome. This would be their observed data point. That's actually recorded in your data set. It's what you measured. This is your regression line that best fit your data. And so that's the distance from the line to the data point is your residual value for that data point, right? So you can measure your residuals, and then you can make a histogram of your residuals, and you can look at whether or not they're normally distributed. The smaller your residuals are. Yeah. Yeah, so the closer it is, the smaller the residuals are, the less standard error there is. So when one does linear regression, the output you get in the model from Stata is basically, for all intents and purposes, the equation for that line. We don't always think of it that way, but that's essentially what we're getting, right? So you might see in the output that you're given, we'll go back to the age and macular thickness, that the beta coefficient in a linear model is, let's say, minus 0.9, right? So for every additional year of age, you're losing 0.9 microns of macular thickness, would be the interpretation there, okay? So that would be the output we would get from Stata or SPSS. Really what you're doing, though, is you're graphing the best fit regression line, and that's where the beta value is derived from. It's one of the slopes of the line. So we can also look at residual plots. This is a graph of our residual values to look for homoscedasticity. Homoscedasticity is when the residual values are related to our outcome. So we see here, so this is sort of no relation. Our dots, our data points, our residuals are kind of distributed all over the map. There's a few out here, there's a few out here, there's a lot in the middle. But here we can see with increasing predicted values of our outcome that we see the residual values increasing systematically, right? That's something we don't want to see when we're doing regression, because it means that the amount of error, right, the distance from the regression line is related to our outcome, and we don't like that, right? It means that the regression line is actually fitting a certain part of our data better than another part of our data. And we want the line to fit all of our data nicely. So that would be something we would not want to see, and we would want to talk about how we might be able to transform our data or do something to our data or choose a different type of model that's going to fit our data better, because the linear model doesn't seem to fit in this case. So here's an example of a case in which we might use linear regression. This is a paper that we recently published. What patient and caregiver factors are associated with caregiver quality of life in primary congenital glaucoma? So we had a quality of life measure that was continuous. It was on a log scale. And we tested a number of factors in a linear regression model to see which of those factors were associated with quality of life in primary congenital glaucoma. And I guess this came out kind of illegible on the screen here. But what we see is we get our beta coefficients. These are the slopes of our line. Going back to the question from before, we have 95% confidence intervals around those slopes. And here's what we're measuring: child's age, gender, duration of disease, patient age. And so the way this would be interpreted is that for every 1 year increase in duration of disease of primary congenital glaucoma, we see a 0.04 unit decrease in caregiver quality of life, because the coefficient's negative here. Does that make sense? That's how we would interpret the model in this case. And it's up to you as the clinician to decide whether that's a meaningful amount of decrease in quality of life, or whether that's just a small amount that's probably not meaningful. Questions about linear regression before we move to logistic regression? So when it comes to logistic regression, in many ways, the way we think about it is similar to linear regression. It's just that our outcome is different. That's an oversimplification. We'll get into some of the other differences, but we want to model the association between variables when our outcome is either binary or sometimes even ordinal. But most logistic regression, it's binary. We want to predict whether people become blind or not. We want to predict whether people have glaucoma or not, right? It's an all or nothing type thing. Now I put in parentheses here to test the adjusted association, because in logistic or in linear models, when we have multiple variables in the same model, the way we actually interpret the variable, so all of these variables were in the same model, what we do is we say that for each 1-year increase in duration of disease, we see this fall in caregiver quality of life regardless of everything else. Parent age, male gender, child's current age, socioeconomic class. So all of those things are adjusted for in the model if you have all these predictors in the same model. So the interpretation is that any one of these betas that you're interested in is independent of all the other ones. Does that make sense? I see some no's. So, let me think of another way of phrasing it. We could run a model where the only predictor, right? Again, so we're still trying to predict caregiver quality of life here. But let's say the only thing we put in the model to predict caregiver quality of life was this first variable, child's age. Okay? So that would mean that the child's age was the only thing predicting it, and that we allowed for all of these other things, gender, duration of disease, parent age, caregiver education, we allowed them to just follow kind of whatever distribution they follow in our data set, and we're not paying attention to them. And it may be, in fact, that one of these, say we find a significant relationship between child's age and caregiver quality of life. It might not be, however, a real relationship if there's confounding, right? Maybe child's age is affected by parent age, older parents more likely to have older children, but let's say that older parents are also more likely to have higher caregiver quality of life, right? So that might affect the relationship that we report if child's age is the only variable in our model, right? So what do? We put parental age in the model with child's age. And once we have those two variables in the model together, we can look at the regression coefficient for child's age and say that that is the association with our outcome, caregiver quality of life, independent of parental age. We've adjusted for parental age. We've taken it out of the we've put it in the equation, but we've we've taken it out of the equation in terms of interpretation. Okay, better said, we put it in the model, and therefore we've adjusted for its impact on the relationship between child's age and caregiver quality of life. Does that make sense now? Kind of. The same is true for interpretation of any of the other variables that are in that same model. They're all independent of the other variables in the model. So in the equation, what we're doing is inserting a value. Basically, we're inserting a value of 1 for all those things we want to adjust for. And looking at, I don't know if this is going to be helpful to explain it this way, and looking at the remaining beta that is our variable of interest. So we're taking these other variables out of the equation by just giving sort of a standard value of 1. So it's multiplicative, right? So let's say this was parental age, and so let's say this is parental age. This is our slope that relates parental age to caregiver quality of life. If we put a value of 1 there, then we're just adding our slope to everything else in the regression equation. We're not actually adding the impact of a particular parental age. So it's being adjusted for. I don't know if that helped or not. Do you have other questions that'll? No. And actually, in fact, this column right here is the multivariable analysis. That is, the variables that were significant when we tested each one in its own model got then kicked into a model that contained all of those significant variables. So there were 1, 2, 3, 4 that were significant over here. Or conceptually relevant might have been a reason for putting it in the multivariable model. So we put 4 of them in the multivariable model, and we can see that there's a little change in these beta coefficients when you're adjusting for other things. And in fact, socioeconomic class, although this wasn't a significant finding, this is comparing upper versus lower, seemed to have a certain effect in the univariate analysis, but then when we adjusted for some other variables, the effect was actually in the opposite direction. So it suggests maybe there's some confounding there because the effect, the direction of the effect changed. So moving on to logistic regression. So again, we're testing, this is a regression model for a binary or ordinal outcome rather than continuous outcome. In addition to assuming that the data fit one of those types, ordinal or categorical or binary, this model also assumes there's little multicollinearity. That is, our predictor variables are not strongly correlated with one another. It assumes that the observations are independent. And this is the tough one where math comes into it. The independent variables are linearly related to log odds. I don't think it's worth getting too into that, but I'll show you a little graph that maybe will help a little bit. If we have a binary outcome, there's just 2 options, right? So we're not going to have data all along a regression line like that, right? Because there's only 2 options. The data are either going to be down here or they're going to be up here, right? Yes, they're blind. No, they're not blind. There's no space in this for partially blind, right? It's binary. So all our data is up here or all our data is down there. It does us very little good to try to make a linear model where we fit to all of these yeses and all of these nos, right? That's not a good model of what's going on in our data. That line does not hit many of our data points. What about that line? That line hits a lot of our data points, right? It's more sigmoid function. So we need a different equation to draw a line that's going to hit binary data points, right? Essentially what we're doing is we're mapping out probabilities, the probability that you're up here versus the probability that we find data down here. And so the regression line equation winds up having a log term, but this right here, people say the odds of my flight being on time are not very high, right? It's raining. When people say odds, or if people gamble, they say there's the odds are 5 to 1. What odds really are the probability of an event divided by 1 minus the probability of that event. That's just the definition of what odds are. This equation, this side of the equation, you'll notice is the same as our linear regression equation, right? We have an intercept, we have a slope, we have space for our coefficient values to be placed in there. Hi, Ashok. But over here, over here, our outcome varies, right? We're looking at odds. We're looking at the probability over 1 minus the probability, the definition of odds. And we use this natural log to transform that into a sigmoidal function so that we meet our no answers and our yes answers, right? Our binary answers, yes or no, right? Without that log transformation, we're going to have a straight line, and it's not going to fit our data real well. So this is an example of something we published that used logistic regression. These are all adjusted odds ratios. So you end up getting an odds ratio out of a logistic regression model. That means a ratio connotes that we're comparing something, right? Back here, we were talking about this being equivalent to just odds. We never said the word ratio back here. So for a ratio, we need to compare 2 things. We need to compare the odds for males as compared to the odds for females. We need to compare the odds for people who are 57 compared to people who are 58, right? A 1 unit increase in age. right? What's the change in odds as we get 1 year older of some outcome, of blindness, let's say. So here what we were modeling was whether or not, this is the same study we talked about before, whether or not older adults had received eye care in the past 2 years. That was our outcome. They either got it or they didn't. So it's a binary outcome. So the result of our model, it's a logistic model, is going to be an odds ratio. So what we would say here is that females had 2 times the odds that males had. So it's a ratio. So one of our groups is going to have the value of 1. We're going to set it to 1, and we're going to look at how another group compares to that one, right? So we could have said, let's set females to 1 and see what happens with males. We arbitrarily said we'll set males to 1 and see what happens with females. Females had 2 times the odds of males. If we flipped it, we would say males had half the odds of females. We have a confidence interval around our odds ratio. We can look at, I don't think I included any continuous predictors here. In fact, age we also categorized, 50 to 64 and then 65 to 80. But if you had a continuous predictor, like let's say we had age as a continuous predictor, we might interpret it as the odds per unit increase, the change in odds per unit increase in age. So we would be comparing, say, 68-year-olds with 67-year-olds and saying there's a 1.1 times the odds for 68-year-olds that there are for 67-year-olds in getting an eye exam. So you can enter a continuous predictor, you can enter a categorical predictor, and the interpretation is roughly the same. But you're looking at a ratio of odds for one person versus odds for a different person or a different group of people. Questions about that, about interpreting logistic output? So I'm just going to go quickly through a couple other types of analysis. I'm not going to get into the assumptions or too much of the math behind it, but just so you've seen it and you're familiar with different types of analysis. Sometimes we want to know when people meet a certain endpoint. In a lot of non-ophthalmic studies, that endpoint is death, survival. In a lot of our studies, it might be blindness or vision impairment. In this case, we were looking at the likelihood that somebody, the probability that somebody along our study reported being depressed. So we had 2 groups of people, vision impaired and non-vision impaired, and we wanted to know over 6 years, did the vision impaired people, our hypothesis was those people who were visually impaired were more likely to have onset of depression. And so we used the survival curve to look at, in blue, the people without vision impairment, in orange, the people with vision impairment, and this is the proportion of respondents who have remained depression-free. And we see separation of the lines in that those with vision impairment, as we get out to round 6, actually have quite a bit of depression as compared to those without vision impairment. Survival analysis is helpful when you have a binary endpoint. They get depressed or they don't get depressed, right? Binary endpoint. And you have different length of follow-up. Not everybody was in this study for the same amount of time. And survival analysis is a good way to deal with that. Typically, we'll put these tables down here that let us know how many people in each of the group were at risk for the event. That is, how many people kind of remained in each group as these lines tick downward. And it just helps you to interpret the analysis to know how many were at risk for that particular event that you're studying. Questions about survival curves, survival analysis? And these are called Kaplan-Meier survival curves. And oftentimes one of the statistics we'll use for survival analysis is called a hazard ratio, which is, for all intents and purposes, interpreted quite similar to, say, a relative risk. We can also do mediation analysis. This goes back to that diagram that we looked at before where we were talking about the value of drawing lines between our variables and thinking about the relationships that might exist. So we figured that perhaps there's a relationship between, we wanted to get more into why is there a relationship between vision impairment and depression, not just that there is one. So we wanted to test a pathway. And so we're hypothesizing that this pathway here, through health-related disability or through restricting one's social activity, helps to explain why people become depressed. And so there are different ways of doing mediation analysis to test whether or not this is in fact the answer, if this is the pathway that this phenomenon exists through. And it's really helpful to have longitudinal data to do this because you want to know that your exposure vision impairment came before your event, because otherwise your arrows might actually be in the other direction. And we don't need to get too into what the statistics are to do mediation analysis, but you can use a combination of regression models, or you can use something called structural equation modeling. And then there's different ways of analyzing survey data. Oftentimes we use something called rash analysis or item response theory to analyze survey data and look at how well the survey data is matched to our sample. Right here what we're seeing is that the difficulty of certain items in this caregiver quality of life survey that was given to caregivers of kids with primary congenital glaucoma in Madurai, the difficulty of those items was matched really well to the caregivers. And so we think this is probably a pretty good test for us to be using for this and a variety of other reasons. But the rash model and rash analysis allows us to take a look at this and also to take a look at a number of validity and reliability and precision statistics. That gets back to that validity type of test that we talked about at the beginning, or sometimes we say psychometric test that we talked about at the beginning, to evaluate a measure. Gets to its measurement properties, and that's one way of doing it. We also have agreement plots. So again, let's imagine that we have two graders, or perhaps we have two instruments. We want to know how well eye care is related to Goldman applanation tonometry. So we can graph using what's called a Bland-Altman plot or an agreement plot. We can take the value of one test minus the value of another test and the mean of the tests and plot them, and we can see how much agreement there is within our 95% confidence intervals, and it allows us to see whether or not we think these tests are approximating one another or whether there's poor agreement between the tests. So there's all sorts of different statistics we can do to explore these more nuanced questions that may not be amenable to sort of simple t-tests, chi-squared tests, or even things like linear or logistic regression. Questions about any of those statistical tests or methods, or what test you might use for a specific question that you have? So I know everybody's getting a little tired in that after lunch lull, but I thought maybe we could try just looking at a couple examples, and if people want to help me to interpret some of these examples, maybe that'll be a useful way to kind of wake up and stay engaged. So I'll describe what we have here. We have different age groups, right? Categories, 65 to 69, 70 to 74, etc. We have men and women, right? Another variable, sex. And some of these people don't have vision impairment, and some of these people do have vision impairment. And we want to know if the distribution of vision impairment, no vision impairment, differs by age, and we want to know if it differs by sex. What test do we use? I heard I'm sorry, chi-squared? Yep, exactly. So we use a chi-squared test, and we found that there was a difference, right? Not surprising. There's a lot more vision impairment in older people than there is in younger people, and we can see that because 3.3% of the over 90 crowd did not report vision impairment, but 13% did, right? So big difference right there. And as we get down here, the difference is in the other direction. And we tested it, and that was significant. Similar pattern when it came to men and women. So this is the study on caregiver quality of life in primary congenital glaucoma from here in India. And what we wanted to know was whether or not low caregiver quality of life and high caregiver quality of life differed by, or I should say, whether mean age of the child, age at diagnosis, and caregiver age varied depending on whether or not they were in this low category or high category. And we just split the data in half and said we have 70 data points. Let's take the 35 high data points and call them high, the 35 low data points, call them low. Is the age of children different between the low and the high? So what test do you use? You could, but you can be simpler than that. So why paired? So in this case, it wasn't the same. So the people over here that were defined as low caregiver quality of life are different from the ones that are high caregiver quality of life. It's two samples essentially, right? So you have half of our sample we've defined to be low, half we've defined to be high. If we're going to do a paired test, they should be actually the same people, right? So so I heard somebody say a two-sample t-test. That's exactly right. So we used a two-sample t-test, and we found that there was no difference in the age of children, age of diagnosis, or caregiver age between those with low and high caregiver quality of life. All right. So third example. So what we have here is, this is not a study I was involved in, but it's the effect of changes in vision on activity limitations. So we wanted to know, or they wanted to know, I should say, these are the outcomes actually listed here, and they wanted to know for fair or poor vision, or for, over here, legal blindness, what happened with disability. And so what do we, what test would we perhaps use here? I'm going to say they modeled it actually the other way. So this is, let's say this is the outcome. Fair, poor distance vision, right? So you have it or you don't. You either have fair or poor distance vision, or you don't have fair or poor distance vision, right? So logistic regression, right? Yeah, so can somebody interpret, so this was a significant odds ratio right here, that's 0.57. Can someone interpret that? What does it mean, the 0.57? Yeah, so I think, so I believe what's happening here is that for those people with fair or poor distance vision, they had half the odds of being able to make a phone call, or if it was modeled the other way, and I honestly don't know which way it was modeled, we could say if you're able to make a phone call, you have half the odds of having fair or poor distance vision. But I think it's probably the other way around, because you'd expect the people with poor vision to have trouble. So I think they modeled it the other way. So the same is true when it comes to legal blindness, right? We interpret it the same way. If these were all in the same model together, we would say independent of everything else in the model, this is what we're seeing. I think that was my last example. This is a really nice resource, though. It's a online course that was funded by the National Institutes of Health on doing peer review. And so the target is journal reviewers, but it really gets into a lot of relevant topics to what I've been talking about today. Study design, is it appropriate for the question? How do we look at measures of association, when to use correct measures of association, and disease frequency. And it's all available online for free. They're all relatively short. I think they're an hour a piece lectures. They're well done, and even though it's geared towards peer review, I think it's really relevant if there's a concept there that you want to dig a little bit deeper into, to watch some of these free online videos. And it's through, as you can see, through the Cochrane Group. And so I'd like to just acknowledge these people and organizations for their contributions to the presentation, and to thank Drs. Venkatesh and Kavita